Hey everyone, welcome back to Mind Maths with Amina. We are going to solve more questions given in chapter 5 called Functions of Several Variables. This chapter is in the Mathematics 1 study guide given by University of London for their EMFSS courses. Okay, the question is that they want us to show that the only critical point of this function is at the origin. They want us to consider function when y is equals to 0 and at x is equals to 0, or otherwise determine the nature of this critical point. Okay, so the function f(x,y) is x power 4 minus x squared y squared minus y power 4. So the derivative of f with respect to x is going to be a 4x cubed minus a 2xy squared, and we want to put it equals to a 0. So we'll get a 2x will be equals to 2x squared minus a y square is equals to a 0. So we get a 2x is equals to 0 and 2x square minus y square is equals to 0. So x is equals to 0, or 2x square is equals to y square. So an x square, let's just write it like this, x squared is equals to y squared by 2. So x is equals to a plus minus y and under root of 2. Okay. The partial derivative of f with respect to y is going to be a minus 2x square y minus 4y cube is equals to a 0. And when we take 2 minus 2y as common, we'll get x squared plus 2y squared is equals to a 0. So we get a minus 2y is equals to a 0, which basically gives y is equals to a 0. And over here we get minus an x squared is equals to a minus 2y squared, which would give us complex number, which is not allowed. So this is going to be undefined in the real plane. Okay, so which means we need to solve this, all combinations of these actually. So we have to solve equation 1 and 3, and we have to solve equation 2 and 3. So equation 1 and 3 basically tell us that the critical point is x is equals to 0 and y is equals to 0. And 2 and 3 tell us that 3 tells us when y is equals to 0. When we put this in equation number 2, you'll get plus minus 0 is just a 0. So yeah, we have just one critical point. The critical point is when x is equals to 0 and y is equals to 0. So now let's work out the Hessian. So the Hessian matrix basically helps us tell the nature of the critical point when we're working with functions of several variables. So this should be the first entry is fx with respect to x, then x with respect to y, then y with respect to x, and f y with respect to y. Remember that let's call this matrix H. Okay, so whenever we have a negative definite matrix, which means fx with respect to x is negative while the determinant H is positive, we're going to have a maximum point Whenever fx with respect to x is greater than 0 and the determinant is 0, so positive definite matrix, we have a minimum point. And whenever the determinant of the matrix H is equals to a 0, then we have a saddle point. And if the determinant is negative, then it's like the result is inconclusive. Okay, so let's write this down. Okay, let's find oh, actually we already calculated fx with respect to x, right? We don't need to recalculate all of this. And we had f with respect to y. So okay, so let's make our calculations here. So fx with respect to x is just a 12x square minus a 2y square, and therefore at the critical point it's just going to be is equals to a 0. Fx with respect to y is going to be a minus 4xy, and at the critical point it's going to be equals to a 0. Oh, now it's quite obvious then that fy with respect to x is basically, it's all going to be a 0. So this does kind of suggest a saddle point. Anyhow, let's continue with the working. Fy with respect to x is a minus 4x y, and it's a 0. And fy with respect to y is going to be a minus 2y minus a 12y. Again, it's y square, sorry. And this is again, where did I ate the x square, right? 2 minus 2x square, and yeah, this is again going to be equals to a 0. So the Hessian has all entries being equals to a 0. So the determinant is a 0. So basically this suggests a saddle point, or you could say like an inflection point. Another way that we can find this is by observing how the graph behaves when one point is at the critical value. So suppose x is equals to 0 and y, we just keep it variable. Then we'll have a minus y power 4, which in the two-dimensional plane would look like this, right? So at when we take the limit, or let's not talk about the limit, this graph has a maximum point when we take y is equals to a 0. Okay, and when we keep x variable and we put y is equals to a 0, we'll get an x power 4, which in the two-dimensional space looks like this. So in this graph we have a minimum point at x is equals to a 0. So as you can see, like the behavior around this doesn't basically match, because in one contour basically gives us indication towards a maximum point, and another tells us section, maybe, what is it actually? Suppose this is x, this is y, and this is the function fxy. So if we take x is equals to a 0, so yeah, sorry, we're talking about sections then. So when we see what's the behavior, this is a section. This section actually gives us a maximum point in this section. gives us a section is basically a two-dimensional representation of whatever this surface was over here, whatever this three-dimension thing was. So a section is just a two-dimensional shadow or two-dimensional representation of this three-dimensional space. The section itself, both sections are giving us contradictory conclusions. So therefore, we don't have either a maximum or a minimum. We have a saddle point. Okay, next question. Find the critical points of the function this. Okay. f(x,y) is equals to x cube minus y cube minus 2xy plus a 3. Okay, f(x), f with respect to x, putting it equals to 0, is a 3x square minus a 2y is equals to a 0. So we have a 2y is equals to 3x square. This is going to be our equation 1. Then we take the derivative of f with respect to y, which is going to minus 3y square minus 2x is equals to a 0. So over here we're going to get a minus 2x is equals to 3y square. This is my equation 2. I need to solve these two simultaneously. Okay, so in the first equation we have 2y is equals to 3x square. So from 2 we can plug in the value. Okay, so from 2 we know that x square is going to be a 3y square over a 2, a minus 2, and we want to take a square of this. Basically I've made x the subject over here, which is a 3y square over minus 2, and we want its square. So we'll have a 3 into 3 3s are 9 y power 4 over a 2 power 2 is just a 4, and we have a 2y here. Okay, so we'll end up with 2y minus 9 3s are 27 by 4 y power 4 is equals to a 0. We can take 2y out as common. We'll get a 1 here. We'll get a 27 over 2. Actually this will become a y cube, and this will become an 8. Okay, and so we have 2y is equals to 0. So one possible value is a 0, and the next one would be a 27 over 8 y cube is equals to a 1. 27 y cube is equals to an 8. So y is equals to 8 over a 27 over 1 by 3. So we can write 8 as 2 power cube, right? What about 27? Yeah, I'm going blank. 3 3s are 9, 9 3s are 27. Oh, yeah. Sorry for sounding dumb. So we're gonna have a 2 by 3. Okay, so let's find out our value of x. Okay, so the value of x, okay, when y is equals to a 0, x is going to be equals to 0. And when y is equals to a 2 by 3, then y square is going to be equals to 4 over 9. Therefore x is going to be equals to minus 3 by 2 multiplied by a 4 over 9, which is basically we have 3 3s are 9 and 2 2s are 4. So we have a minus 2 by 3. So we have two critical points. One critical point is the origin. So we'll need to see the value, see the nature of the Hessian at the origin. And the next one is a minus 2 over 3 and a 2 over 3. Okay. And determine whether it is a local minimum, local maximum, or a saddle point. For that, we do need the Hessian. Okay, so the Hessian is going to be a matrix f(x) with respect to x, x with respect to y, fy with respect to x, y with respect to y. And because the Hessian is a symmetric matrix, therefore fx with respect to y is going to be the same as fy with respect to x. Okay, so let's find out these value of these. Okay, this was my f with respect to x. Okay, f with respect to x. So we needed fx with respect to x, which is simply a 6x. Fx with respect to y is a minus 2. Okay, what about fy? This was fy. Okay, this was fy. I want fy with respect to x, which is a minus 6. Oh no, fy with respect to x is just a minus 2. And if fy with respect to y is a minus 6y. Okay, so the Hessian is a 6x minus 2 minus 2 minus 6y. So the determinant of the Hessian is a minus 6 is 36 into xy minus a 4. Okay, so let's write down how we classify the critical points. If fx with respect to x is greater than 0 and the determinant of h is also greater than 0, then we have a local minimum. If fx with respect to x is less than 0 and the determinant of h is greater than 0, then we have a local maximum. Whenever the determinant of the matrix is negative, then we have a saddle point. And whenever the determinant is equals to a 0, then we have an inconclusive output. Actually, didn't I mess up the previous one then? Yeah, I should have actually wrote over here that the determinant of h is equals to a 0. It's not a saddle point. Sorry, guys. This should be inconclusive. Yeah. So let me confirm this. This actually does give us a contradiction over here, so maybe yeah, it is inconclusive. It is, but it looks like saddle from here. I'll see the solution and verify this. Let's just see it. This was question number, what was it? Question number 5.5. Question number 5.5. Okay. Maximizing when do I not? It is a saddle. Okay. Yeah, well, that's the confusing. It is a saddle. However, of course, as usual, and it fails here, which is precisely the point. However, the question tells you how you should analyze the nature by considering. Okay, that's kind of a bit of a contradiction because it's, if we do it the way they're asking us to solve it, it gives us a saddle path. But if I do the second derivative test, which is basically analyzing the Hessian, determinant of the Hessian, then the result is inclusive. So what we should do is, whenever such a situation arrives, then what we should do is that we should analyze the function where we take x as it is and we put the critical value of y and we observe if this gives us a minimum point or a maximum point. So we look at this behavior and then we take x at its critical value and y as it is, and we see whether this section gives us a minimum or a maximum. If both of them give us the same conclusion, then we will say it's a local minimum. If both of them say that there's a maximum, then we will conclude a maximum. But if one says a minimum and the other says a maximum, then we will conclude that we have a saddle point. Okay, so remember, if the Hessian gives us an inconclusive result, then we shouldn't end the question here. We should see how the sections behave. Okay, moving on. This was just kind of like a recap and was actually nice for me as well, because I haven't studied this stuff since a while now. So this was like a good recap because I keep forgetting stuff. So this was nice for me as well. Okay, so let's analyze the critical point, which was the origin. I think it was the origin. Let me see. Yeah, origin. So fx with respect to x, which was a 6x, becomes a 0. And the determinant of the Hessian will actually become a -4, which is negative. Therefore, the origin is a saddle point. Okay, great. The next critical point was, I'm forgetting because I got a bit detracked. Okay, the next, it was a -2/3, -2/3 and 2/3. When we put it in the first entry, is going to be a 6 into -2/3, which is negative, and the determinant of the Hessian matrix, which is this. Okay, since the value of x is negative, this whole thing is going to become positive, right? So it's a -36 multiplied by -2/3 and a 2/3 -4. This is definitely greater than 0. So therefore, this critical point is a local maximum. Okay, let's move on. Is this the last question? Oh no, we have 2 more. Okay, a firm is the only producer of 2 goods, X and Y. If the firm produces quantities X and Y of X, blah, 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 the corresponding prices are this. Okay. The firm's total cost for producing X of X, and okay, we have the prices. Okay, we have this equation. We have this equation. And we have the total cost. Find an expression in terms of X for the firm's profit. Okay. We have Px minus Py plus 13 minus 6y is equals to a 0. And we have a positive Py minus 4Px plus 26 minus 6x is equals to a 0. So the total revenue, this is a tricky question actually, will be total revenue from selling good X plus total revenue from selling good Y. And this is going to be px into x plus py into y. So let's make py the subject in the first equation. So what will this become? We'll have, but that's the problem. We need everything in terms of x and y. We need to eliminate prices. So let's just solve those simultaneously first. Yeah, let's solve these simultaneously. If I add these up, this gets cancelled and I'll get a minus 3px plus 3679 minus 6y minus 6x is equals to a 0. We have a 3px is equals to 3 1s are 3, 3s are 9, 3 2s are 6, equals to 0. Okay, so now we have px solely in terms of x and y. That's how I needed it to be. Okay. Before I proceed, I should probably check if I'm doing the right thing or not. 5.7. 5.7. Is this what we got? 13 minus 2y. Oh, yay. Yeah. And then py. Oh no, my baby's awake. I'll be back. Okay, then we need to find the price of y in terms of quantity x and y. What we can do is we can just put it in one of the equations. Let's put it in the first one. So it'll be a 6y minus a 13. Oh no, actually, py is equals to px plus 13 minus a 6y. Okay, and then we'll have a 13 minus 2y minus 2x plus 13 minus a 6y. So price of y is 26 minus 2x minus an 8y. Okay, so coming back to the total revenue is price into quantity. So price of x is this, and we multiply it by quantity of x plus price of y, which is this. We multiply it by quantity of y. I want to avoid the product rule, so I'm just going to open this up. 13x minus 2xy minus 2x squared plus a 26y minus 2xy minus 8y squared. Okay, we can simplify this further actually, I think. Can we? Yeah, we can make this into a 13x plus 26y minus 2x squared minus 8y squared and minus 4xy. Okay, now the profit as a function of quantities is total revenue, which was this, and the total cost function was given. It is a x plus 2y. So we need to subtract this, so it's going to be minus x minus 2y. Okay, the profit function then becomes a 12x minus 2x squared minus 4xy plus 24y minus 8y squared. Okay, so let's take the partial derivative of the profit function with respect to x. It's going to be 12 minus 4x minus 4y, and we need to put this equals to a 0. Okay, we'll get 4x plus 4y is equals to a 12, which becomes x plus y, and 4 3s are 12. So this becomes my equation 1. Okay, then I take the partial derivative of the profit function with respect to y, and that's going to be 26. Right? No, where is it? Wait. This is the profit function. Okay. So we'll get minus 4x plus 24 minus a 16y. And we need to put this equals to a 0 because we need to find the critical point. And this will become a 4x plus 16y is equals to a 24, which is a x plus a 4y is equals to a 6. So we need to solve equation 1 and 2 simultaneously. So we have an x plus y is equals to a 3, and a minus x minus 4y is equals to a minus 6. So we'll end up with a minus 3y and a minus 3. Therefore, y at the critical point is going to be equals to a 1. Therefore, x, from equation 1, we can see x is equals to 3 minus y. So 3 minus 1 is equals to a 2. So our critical point, which we will later need to classify, is a 2 and a 1. So a 2 and a 1. So now let's write down our Hessian. The Hessian matrix has the partial derivative of x with respect to x, then x with respect to y, then y with respect to x, and y with respect to y. Okay, I think we're looking to maximize profit. So what we want is the partial derivative of x with respect to x to be negative, and we want the determinant of the Hessian matrix, which is basically x with respect to x multiplied by y with respect to y minus xy whole square. This is symmetric matrix, therefore these two partial derivatives should be the same. We want the determinant to be greater than 0. If this happens, then we can say that we have the profit is being maximized. Okay, so let's go to these two. We've already found these. So we had the, let me write it like this. We had the partial derivative with respect to x and the partial derivative with respect to y. We need x with respect to x, which is a minus 4, which is actually negative. And then we needed x with respect to a y, which is a minus 4. Then we needed y with respect to x, which is a minus 4. And then we needed y with respect to y, which is a minus 16. Okay, so the Hessian basically then becomes a minus 4, a minus 4, a minus 4, and a minus 16. The determinant of this matrix is going to be a minus 4 into a minus 16 minus a minus 4 into minus 4 is just a positive 16. So we have a 16 multiplied by 4 minus a 16, which is basically 16, 4 minus 1, which is a 16 into a 3, which is greater than 0. So yeah, we have the determinant is greater than 0, and therefore we do have a maximum point. Okay, moving on to the next question, and I think this is the last question for this video. Suppose that a constant a is a positive number and that the function f is given by this. Okay, find the critical points of x. Okay, so we have f xy is equals to x power 4 minus 2a square x square minus y square plus a 1. So the derivative with respect to x, the partial derivative, is going to be a 4x cube minus a 4a square x, right? And the partial derivative with respect to y is just a minus 2y. So when we take the partial derivative with respect and we put it equals to a 0, we get this expression equals to a 0. If I take 4x out as common, I'll get a x square minus a square is equals to a 0. So we have either a 4x is equals to a 0 or x square is equals to a square, which is x is equals to plus minus a. Okay, so this gives me x is equals to 0. So we have 1 here and an x is equals to a and a minus a. So we have a 1. Let's just call it 1 prime. Oh, no, let's call that 1 prime and 1 double prime. Okay. Then we have fy is equals to a 0, which will give a minus 2y is equals to 0. So y is equals to a 0. This gives me 2. So we have to make combinations of all like 1 and 2, then 1 prime and 2, and 1 double prime and 2. So the first critical point is a 0, 0. Then we have an a 0, then we have a minus a 0. So we have 3 critical points that we need to classify. Let's take the double derivatives. Okay, so fx with respect to x is a 12 x square minus a 4a square, and fx with respect to y is basically a 0. Okay, then fy with respect to x is a 0 and fy with respect to y is a minus 2. Okay, so therefore the Hessian matrix is, this is the first entry, this is we have a 0 and a 0 here and a minus 2 here. Okay, for each critical point, determine whether it is a local minimum, maximum, or saddle point. Okay, the determinant of the matrix is equals to a minus 2 into a 12x square minus 4a square, and the first entry is this. Okay, so let's analyze the critical point which was the original. So the critical point 0, 0, the first row and first column entry ff is basically a minus 4a square, which is going to be negative, and the determinant of the matrix will become a minus 2 into a minus 4a square, which is positive. Therefore, this suggests that at the origin we have a local maximum. So this is going to be a local maximum. Okay, moving on. The next critical point is, let's do a and 0. A and 0. Okay, so the first entry becomes x is an a, so we have, oops, let me erase this. X is an a, so we have a 12x square minus, a square minus 4a square, which is actually a positive number. because it's going to be a 8, 9, yeah, 8a square. A is a positive. I think it's told us that A is a positive number. Yeah, so this is greater than 0. What about the Hessian? That's the determinant of the Hessian is this. Which is basically a -2 multiplied by an 8a square, which is negative. So therefore this means that we have, because the determinant is negative, we have a saddle point. Similarly, when the critical point is a -a and 0, the first entry is going to be a 12. Actually, it's going to be the same because a -a square is just going to be a positive a square. So this is again 8a square, and therefore even the determinant is going to be the same. So both these points are saddle points, whereas the origin was a maximum point. So this is a saddle point. So this was my last video on chapter 5 of this Mathematics 1 study guide, and I think the next chapter is about matrices. So the next few lessons, maybe 5 videos, will be me solving questions on matrices. I hope this class was beneficial to you, and I will see you in the next one. Take care.